welcome, morning in Taiwan and evening in Indiana. And I hope that, Cliff, you have seen the film, The First Man. That's coming from the,
yes.
Yeah, the title song. And we are very happy today. We have Professor Cliff Neal to give a talk at this online seminar. He will talk about the Lunar Institute resource utilization. But before he gives the talk, I want to say a few words about to introduce Professor Neal. And as you will discover later, very soon, he is from England, and because he got his bachelor degree from Leicester, right? And then they got your PhD in Leeds, and you're a geologist, or mineralogist, in training. So he keeps his basic training but move the place to the moon. That's all. And if you go to his CV, you'll find he has a long string distinguished career, and then in particular, he's very active in NASA's lunar science activity. I would say technology. And I will introduce you, lead you to read the paper, recent paper written by him in Scientific American. The title is "Shooting for the Moon: This Time to Stay." You can see he's a very enthusiastic person. And I mean, with this, I think that we really want to know, what he had to say. Okay, good. Please start.
Thank you very much for that very generous introduction. I don't know about distinguished, but it's been a lot of fun. Let me put it that way. And I have been a very lucky man to be involved in lunar activities for coming on 35 years now. And I saw the first 12 humans walk on the moon when I was a young lad, a young child growing up in the UK. And my father got me up at 4 in the morning in 1969 to make sure I watched history in the making. And I really didn't want to get up, but I'm glad he made me do that. So you can blame my dad for getting me set on this path at the age of 8. But I wanted to thank you for the invitation to come speak to you today about lunar in situ resource utilization. And for many years, talking about lunar resources has been something that has been viewed as more fiction than fact. And this is something I think that has changed, at least in the last 5 years, most notably with science discoveries. And science has been driving my passion for the moon, because we need the data in order to make informed decisions about allowing humanity to actually live and work successfully on the moon and maybe beyond. And the materials that we have, informed by the Apollo sample return, the Soviet lunar sample returns, now the Chinese Chang'e 5 sample return, as well as lunar meteorites, is showing us that there are materials on the moon that become very important for utilization in order to make human stays on the moon sustainable, and I would even say permanent. So this is going to be a rather quick trip through what we have learned from science about resources, lunar resources, and what is the most important critical next step in order to enhance our understanding of these resources. But it all starts with the surface of the moon. And the surface of the moon has been shaped by volcanism and asteroidal and meteoroidal impacts, such that we see a lot of modification to the surface, resurfacing through volcanism, the formation of impact craters and basins, as you can see on the top left diagram there, with the near and far sides taken by Lunar Reconnaissance Orbiter. And you can see the big basins on both sides of the moon that show that the moon has been basically under attack since it formed. Today, there is no atmosphere, although there is a very tenuous exosphere. So it's not a true vacuum, but there are molecules around, but they're so few they don't bump into each other, so they don't get excited close to the surface of the moon. So it's called an exosphere. And this bombardment from macro and micro meteoroids and asteroids, solar wind, cosmic radiation has led to the formation of regolith, as you can see in the bottom left there. And that regolith is basically a feedstock of almost all resources that have been identified on the moon. The breaking up of rock that is often done in terrestrial mines, the crushing and grinding, has already been done by natural forces on the moon. So we're a step ahead in that process of actually getting to use those. So the regolith of the moon is made up of various different rock and mineral fragments, as you can see in the top center diagram there from the Apollo 11 regolith that was brought back. But these glasses that are there, these impact melts, are called agglutinates. They actually are they're glass bonded materials because the glass actually welds together these different fragments. And you could see in at the bottom at the center there, the 10084 sample of an agglutinate, that this agglutinate actually has vesicles in it. It has bubbles due to gas escaping. So we knew back when the Apollo 11 samples came back that there were volatiles on the surface of the moon, but these actually are solar wind implanted volatiles, such that when you get the impact and that melting of glass, it actually produces a reduction reaction, such that iron oxide that's present in the minerals is reduced. You get oxygen and you get iron metal. And you can see in the bottom left the nanophase iron coating. That's a 10 nanometer. I don't know whether you can see my cursor, but there's a 10 nanometer scale bar in the one on the right, and then there's a 20 nanometer scale bar in the one on the left. And this nanophase iron becomes very important for understanding the maturity of the regolith itself. Now, why is this important? The longer that a regolith is exposed to the solar wind, the more mature it becomes. And that means it contains more volatiles. So not only do we get this iron oxide reduction, there's also mobilization of solar wind particles to give you those vesicles or those bubbles that we see in the agglutinitic glass. So regolith maturity then is actually measured as a ratio of metallic iron, or that nanophase iron, to iron oxide in a regolith sample. And it is a percentage measure. So the more it's exposed, the more nanophase iron that regolith has. So the ratio will increase of metallic iron to iron oxide. And this can be quantified by ferromagnetic resonance. So what you see in the bottom left here is this maturity index, affectionately known as I sub S over FeO, against hydrogen. And hydrogen is a solar wind implanted species. And you can see a positive correlation between hydrogen and the maturity. So a positive correlation showing the more mature the regolith is, the higher quantities of hydrogen it has through solar wind implantation. And you can see the big diagram on the right that shows you what happens as regolith becomes more mature. The number of fragments actually decreases because they actually get smaller, and then we end up getting more agglutinates because of the impact processing that goes on as well. Now, I want to start off with regolith, as I said, because regolith is our feedstock. No matter what resource you're going to focus on, because of the surface bombardment and the grinding up of rock to form the regolith, this is something that is important to remember as we go through. So what I've done in this talk is actually divided it into two types of lunar resources. Now, the talk says lunar in situ resource utilization. But there's those that can be for used on the surface of the moon, but there are those that can be gathered on the surface of the moon and then used for potential export, either back to Earth or to orbiting stations for life support, and most importantly for rocket fuel. So again, if we're going to look at in situ resources, the regolith itself is important actually for 3D printing and habitat construction. There's polar water ice and other water yielding resources for life support consumables. And then the regolith contains much more than just volatiles. It also contains metals, and maybe we can say that oxygen is the one reserve we have on the moon. Now I'll get into the definition of resources and reserves, because when we talk about lunar resources, the term resource is being used sometimes when they mean reserve. It's a very pedantic way of talking about it, but it's very important. Other resources could be used spacecraft as well. The tanks could be used to store potential volatile consumables. Lava tubes are the other one. And I'm going to talk about all of these except for the used spacecraft, which aren't really a lunar resource. They're more of trying to use the waste material that took the humans back to the moon. So if we look at the regolith then, regolith is key to understanding our resources. And what we see in the big diagram on the right-hand side is the Highlands regolith from Apollo 16. We have a low titanium basalt from Apollo 12 and a high titanium basalt from Apollo 11. But what you notice in each one, no matter where you go, the quantity of oxygen in the regolith is pretty much the same, no matter where you go on the moon. So we have, if we can extract that oxygen that is bound up in the minerals and rocks in the regolith, then we have life support consumable, or we have an oxidizer for our rocket fuel. And this is something that has been known for many years, ever since the Apollo missions returned their samples. But this is something now that's taking on new significance when we talk about actual resources. The other thing you see there is the number of metals you can get out of the regolith, especially in high titanium basalts. We get titanium metal, as well as we can get iron, of course. These are very good strengthening materials for habitat construction. And also, I have to point out that titanium is bound up in this mineral ilmenite. I don't know how many geologists we have, but this is iron titanium trioxide is the chemical formula for ilmenite. Now, ilmenite is a significant mineral when we deal with lunar resources, not just for getting titanium metal and iron metal Okay, so again, if we look at the regolith that's been exposed to the solar wind, i.e. it is mature, it has been bombarded with these solar wind volatiles. And this mineral ilmenite that you can see here in the equation, iron titanium trioxide, this is a sponge. This has an ability to hold on to implanted species much better than other minerals on the moon. So so if you agitate lunar regolith, you actually liberate quite a bit of the solar wind implanted volatiles. But if it's ilmenite rich, it will hold on to much more. And you could see what happens with solar wind implanted hydrogen. If you heat up titanium rich regolith in a vacuum, and I've seen this done at Johnson Space Center in Houston. You heat it up in a vacuum, you will watch water fall out of the bottom of the reaction vessel, because you get that reaction of iron titanium trioxide plus hydrogen gives you iron metal, titania, and water, H2O. You can electrolyze the water to liberate oxygen, and then recycle the hydrogen into the process. So the transporting regolith to be able to use this will liberate some of those solar wind implanted volatiles. but ilmenite is holds on to them much better. So ilmenite-rich regolith, and you can see in the bottom right here, the Clementine titanium map on the lunar near side has abundant titanium-rich regolith with which to focus on. The other things that have happened here in the top right, you can see pictures of the Apollo 17 orange and Apollo 15 green glasses. And it was 37 years after Apollo 15 greens were collected that Alberto Sal actually showed that these volcanic glasses contained volatiles, and they showed a diffusion profile from the center of these little glass beads to the rims, showing that the source region contained significant volatiles, and this was then substantiated by Eric Howry, and their work suggested that at least portions of the upper mantle on the moon were just as wet as the upper mantle on Earth. Now, once this discovery had been made, and Ralph Millikan and Shuai Li used the Moon Mineralogy Mapper data that a Moon Mineralogy Mapper was carried on the Indian Chandrayaan-1 mission to then look for the hydration signature in pyroclastic deposits. And they found significant pyroclastics. The green arrow is obviously not going to Aristarchus. That's where it should be. And upwards of 0.03 weight percent H2O. And these are what are termed regional dark mantle deposits, i.e. these are massive outpourings of pyroclastic materials. You don't see the Apollo 17 or the Apollo 15 vents shown because these are much smaller eruptions compared to those at Aristarchus and Rima Bode RB there. So this is another potential resource depending upon the size of the deposit. Go to the next slide. Other areas of interest were actually theorized to be present. This was the poles of the moon and having water ice present. And this was hypothesized back in the 60s and 70s, but it was actually shown by Lunar Prospector that there were hydrogen deposits at both poles of the moon because hydrogen is a great neutron absorber. And you can see in the top left there the neutron signatures recorded by Prospector that they went pretty much, really decreased significantly and consistently over the poles, which is what hydrogen does. This has then been substantiated by the neutron detector on LRO, the LEND instrument, and the data suggests that water equivalent hydrogen in the top meter is about just over half a weight percent. So a little bit more than the 0.03 weight percent in the pyroclastic deposits. Now, the LEND data also suggests something that is quite significant. If you look at their data and the way that it's been interpreted, these neutron suppression zones don't just occur within some of these permanently shadowed craters. And to sort of highlight the significance of this, if you take Shackleton Crater right at the South Pole, this has a good neutron signature to it, but you have to go down a 4.5 kilometer, 30-degree slope in order to get to the bottom of Shackleton Crater. But what the data from LEND are showing us is that these suppression zones extend beyond the permanently shadowed regions, i.e. they are around those craters as well as within them. So it is important that to test this and see how much is there by actually doing some ground truth missions to drill down in that top meter to see just exactly how much hydrogen or water equivalent hydrogen ice is actually there, because accessing those permanently shadowed regions and working in temperatures of 40 to 80 Kelvin is quite challenging. And it means that these resources may be out of reach, that they won't be, it will be very difficult to access them. So these represents both science and exploration targets. And it's important to remember that it is not science or exploration, it is science and exploration. The data that you get for science is pretty much the same data as you will get or you will need for exploration, and I'll expand on that towards the end of the lecture. Now, this was supposed to be a transition, so I am going to move this out of the way and just do this for now, and then I'll transition it in. We have one point of ground truth with regards to the volatile content of a permanently shadowed region. The L-Cross impactor was into Cabeus crater, and it's about 5.5 weight% water plus many other volatiles, and that's an important result, because if we are to use the water from Cabeus crater, we are going to need refining capabilities on the lunar surface because the ice is impure, and that is an important important message for planners that want to use the water ice. We're not just mining water ice, we're mining dirty ice, and it needs to be cleaned up. Other important results came in 2018 when Shui Li and co-authors actually looked at surface water ice deposits within permanently shadowed craters from the North and South Pole. And you can see they did this by combining different data sets from M-cubed, the Lunar Orbiter Laser Altimeter, LOLA, and the Diviner, the radiometer. At the South Pole, because the orbit is much lower over the South Pole than the North Pole, they were able to use the UV spectrometer lamp. And by combining those data sets, they showed surface water ice within the pixel size of the M-cube data, which is about 280 meters, present within permanently shadowed craters. So not below the surface, but actually at the surface. And this combination of data sets is really important because it gives us a lot more confidence that the surface deposits are actually real. And this, they modeled, was up to 30 weight% water ice. Now, the skeptics out there actually said, well, that's a frost. That's just a nano layer on the surface being cold trapped, and it doesn't extend to depth. Well, thanks to Rick Alphick and Shui Li, this is now the Prospector neutron maps for the North and South Pole. And the colder colors, the blues and the purples, represent neutron suppression, i.e. presence of hydrogen or water ice. And for the most part, the surface deposits, especially at the South Pole, sit well within the neutron suppression zones. Well, that is important because neutrons actually integrate their data over the top meter. So this extends to at least down into the top meter and requires, again, ground truthing on the surface to actually substantiate that. And that, again, is very important to remember, that these orbital data still require ground truth. We have 1 point so far, and that's Cabeus, but that was an impactor. We need much better fidelity on the spatial resolution of these water ice deposits at the poles. Now, interestingly, another body of work that was published in 2019, it was looking at crater morphologies. Now, there's a depth diameter ratio that shows you or is consistent with these craters. If you know the diameter, you can calculate the depth. Now, we can get the diameter from mapping, but the depth, we needed the LOLA, the laser altimeter data, which we now have. And they found that for, at least at the South Pole, many deposits, many permanently shadowed craters were shallower than they should be using that depth diameter ratio. And they showed that to indicate that these were containing water ice deposits. And this is something that could be up to 10 meters or tens of meters thick in some of these permanently shadowed craters. Again, there's a correlation there with shallow craters and this shallowing at the South Pole, but not at the North Pole. Although we do have evidence of suppression zones at the North Pole, neutron suppression zones, as well as the surface water ice deposits. So some intriguing data on that one. So switching gears a little bit, I want to talk about lava tubes. As you probably know, the diurnal temperature shift, the temperature between night and day, is extremely large on the moon, from almost 200 degrees Celsius in the day to almost minus 200 degrees Celsius at night. It's a little extreme. It's about 180 to minus 120, but it's a huge swing. And if we are to live and work successfully on the moon, we need a habitat that can deal with those temperature shifts. Now, the LRO imagery from the Lunar Reconnaissance Orbiter camera showed many skylights or holes in lava tubes, and these have been proposed to be potential human habitats because the diurnal temperature changes are negligible at those depths. And if you've been in any terrestrial lava tubes, you'll know that it stays cool during the day and it stays cool during the night. The other thing that these lava tubes give you is protection from radiation, and also from meteoroid bombardment. Maybe not an asteroid, but certainly a meteoroid. Now, what you see on the right are results from the Grail mission using gravity to map out the extent of these lava tubes in Marius Hills. And you can see that these lava tubes become quite extensive and extend out laterally from some of these skylights that have been documented by LROC. So this becomes a potential habitat location and therefore a resource, and something to consider as we go back to the moon. Although at least the United States and I believe China and Russia are talking about a South Polar base camp or research station. I think that if you're going to the South Pole to use the water ice deposits, you won't be able to use those within permanently shadowed craters, although we still need to test if they extend beyond the crater walls, as shown by the LEND neutron data. So what about potential export? What resources are potential export? Well, rocket fuel derived from the water, orbital refueling stations, or we can refuel Earth orbiting satellites. This becomes a potential export. Platinum group metals that may have survived from metal asteroid impacts. We know that non-pristine lunar samples have an increase in platinum group elements due to contamination from meteorites. That contamination can be up to several tens of ppm, depending upon the nature of the metal and the amount of contamination that those samples have experienced through impact. But there are some areas that gravity has shown a huge positive gravity anomaly that has been hypothesized to be the presence of or the remnant of a metal asteroid. Whether or not we can reach it still remains to be seen, but by mining the regolith, you can actually mine the platinum group metals that have been deposited there from meteoroid impact. There are also rare earth element deposits. We all need our rare earth elements, especially for electric cars, and the Prosolarum creep terrain is known to be high in creep material, and rare earth elements are part of that acronym. And then finally, helium-3. It's known to be in the lunar regolith from the Apollo samples, And this is the theoretical field for nuclear fusion that yields no toxic byproducts. And I use the term theoretical, although fusion technology has been advancing quite rapidly in the last 5 to 10 years, with multiple minute sustained fusion reactions being attained. And so the Earth, unfortunately, is devoid or is rare in helium-3. There is not much helium-3 down here. But because we have solar wind implantation on the moon contains relatively rich deposits. And Harrison Schmitt from Apollo 17 has calculated that one shuttle cargo bay full of helium-3 coming back from the moon could actually fuel the United States electrical supply for 1 year. So this is potentially a very lucrative export if we can get the technology to work. So rocket fuel, liquid oxygen, liquid hydrogen engines, that's water. Water is the oil of the solar system. The more we look, the more we find water. And the moon was considered during Apollo to be bone dry. And that has since, through analysis of the samples returned by Apollo, that's been shown to be incorrect. It is not. There are some areas of the moon that are just as wet, if you like, as the Earth in terms of the Earth's mantle. So looking at liquid oxygen, liquid hydrogen engines, you can see the red rectangle down in the bottom left. This gives us our most efficient chemical propulsion system. Methane is also used, but it is lower in its efficiency compared to hydrogen. But hydrogen is difficult to store at cryogenic temperatures. It can be done. The space launch system that's being developed by NASA uses liquid oxygen, liquid hydrogen. The Falcon 9 Heavy used by SpaceX uses liquid oxygen, liquid methane. But the problem we have is water is everywhere. And as you see in the title of the slide, water is the oil of the solar system. And it is everywhere, and it becomes a resource not only for life support, but also for export to refuel engines. And reusability becomes important. Unfortunately, the Space Launch System is not reusable. It has not been designed to do that, which I think is a big flaw in development. But that's my opinion, and I'm usually ignored. On the moon, we need a carbon source from Earth in order to make methane if we use water to create the hydrogen and oxygen. On Mars, we need to extract carbon from the atmosphere, the CO2 atmosphere, and combine with hydrogen from water electrolysis in order to create the methane. And it's more processes that we just don't need. So liquid oxygen, liquid hydrogen engines, and Blue Origin over here in the United States is actually using liquid oxygen, liquid hydrogen engines. They are going to the moon with or without NASA, and they are very interested in purchasing the fuel for using from Lunar Resources. Other ones here on the left, we have platinum group metals, and again, looking for metal from meteoroids, asteroids within the regolith, looking at lunar swirls. This could be an iron metal impactor that has got induced magnetism from the impact itself. If you look at the South Pole Aitken Basin in the center diagram here, this is from James et al. 2009. There is a large gravity anomaly that is hypothesized to be the remnant of the SPA, or the South Pole Aitken Basin impactor. And it's because it's dense, it's metallic. So I think this is too deep to actually be used, but the idea of exploring the lunar swirls becomes intriguing to find the remnants of the metal from the meteoroids and asteroids that may have produced these impact-induced lunar swirls. On the right, you see the rare earth elements, and we have the prosolarum creep terrain on the lunar near side that was identified using thorium data from Lunar Prospector. But if it's rich in creep, then it's going to be rich in the rare earths. And the rare earth metals are becoming more and more expensive because the demand increases, it continually increases, especially with the switch to electric cars. So there's another potential lunar resource that could be an export back to Earth. And then finally we get to helium-3. And again, this if you have two helium-3 or a helium-3 and a heavy water, a deuterium, what happens is when you fuse them, you get a helium-4 and 1 or 2 protons. And there's no toxic byproducts. If you take nuclear fission or other potential fusion reactions, you actually do end up with some radioactive or toxic byproducts. But fission is not sustainable because we just can't get rid of the waste. So this becomes a potential target of interest, and there are companies being formed now in the United States to explore the helium-3 mining. I know that some of the Chang'e 1 and Chang'e 2 data sets from orbit were reinterpreted to give you helium-3 maps, which incidentally mirror the titanium map, focusing on titanium as your sponge. And there's interest in this potential export, because if the fusion technology is developed, it then gives an answer to global warming. We don't need to burn fossil fuels anymore. So I want to do a terminology check. I've been talking about lunar resources, and a lot of times people talk about reserves. And I'm just going to say the resource there, the definition I've taken from the United States Geological Survey, references, or the link is down the bottom there, a concentration of naturally occurring solid, liquid, or gaseous materials in or on the Earth's crust in such form that economic extraction of a commodity is regarded as feasible, either currently or at some time in the future. Now, we have identified resources and we have undiscovered resources. So we can use our geologic knowledge. Well, we've found the resource in this type of geologic environment. Well, we know where these environments are. We just need to see if the resource is there. A reserve, on the other hand, is the portion of an identified resource from which a usable mineral or energy commodity can be economically and legally extracted and used. So this is something, economics, you have to do it as a profit in terms of the economics. Now, this is important for sustainability on the moon, that it's not just in the case of the United States, the taxpayer paying for everything, because this can bring in private industry, the mining industry, and they can make a profit on the extraction of the reserve. So the basic take-home message here is resources and reserves are different. And it's important to remember that. And we need to understand a number of things in order to show that we actually have reserves. So we need resources for sustainable human exploration. We need to minimize the amount of material we have to take there to sustain the humans. Again, resources do not equal reserves. And if we want to fully develop lunar resources, I really think we need to have a commitment to permanent human presence on the lunar surface. That way, it's a long-term commitment, and we will be able to get private industry involved, because demand is going to be for the long term. So that requires a multi-decadal plan that transcends politics and national boundaries. What we see with human space exploration, if we look at Apollo was done in a spirit of competition between the United States and the Soviet Union. Once the United States had landed Apollo 11, they had won that competition, and there was no long-term plan for sustained missions to the moon. So less than 4 years after Apollo 11, the program was cancelled, and we haven't been back since. And that is something to remember. If you look at the International Space Station, it has had humans occupying that for now over 20 years. So that is done in a spirit of cooperation. And I really think that as we start looking at lunar resources, exploring these in a spirit of cooperation will enhance a long-term multi-decadal plan. We need to think about the benefit to society on Earth as we do this. So moon technology needs to be transferable to other destinations, including Earth. New mining techniques that develop for the moon could be important here on Earth. But this is important for sustainability because it's a development of a new sector of the world economy. So I think the critical first step is to show that the reserve potential of lunar resources. We need to get to the surface, and we need to get data. We need to go prospecting. Now we can do this with geophysics. We need to understand the regolith, the thickness of the regolith and the megaregolith. So local seismic networks or rover-based ground penetrating radar, as has been shown by the Chang'e 3 and Chang'e 4 rovers, that is a powerful tool to have. We can also use that to look at the thickness and form of polar water ice in some of these shallower than expected craters at the South Pole. The metal deposits can use magnetism and gravity. That's what led us to understanding where they are from orbit. You can see the lunar swirls from Mare Ingenae in the middle diagram, and on the far right you can see the gravity map from the South Pole Aitken Basin. There's also rare earth metals. This is going to be, these can be located through heat flow and also radioactivity because they're in a creep terrain, and where you have a high concentration of creep, you're going to have rare earth elements, but you're also going to have the radioactive elements, the potassium, the uranium, and thorium. And then there's geochemical prospecting. So we need to understand the regolith titania content and maturity. What about volatile abundances and species and different rare earth element metals and minerals and platinum group metals? So that is so surface mobility is needed. We need rovers. NASA has the Viper mission, the Volatiles Investigating Polar Exploration Rover. It's a critical good start to the campaign. But what's next? We need a campaign, not a mission, and we need instruments to quantify surface and subsurface quantities. So I'm coming to the end here. I have a couple of more slides, but I want to show you, using the lunar volatile resources, the types of data that inform science, exploration, and commercial interests. And you can see here the green in the middle is the intersection of all those data sets that become very important for all of those stakeholders. So it's not just science, it's not just exploration, it's not just commerce. It is all three working together to go to the moon to explore and make discoveries and maybe make some money in doing so. So the message, last slide, understanding if resources are reserved is the first step in developing a vibrant and cislunar economy and facilitating human permanence on the moon. So a robotic resource prospecting campaign is essential. Now, I really think this can be international and commercial in nature. And in my spare time, I'm actually drafting a document that would show how this prospecting campaign could be international and commercial in nature. And a variety of instruments are going to be needed depending upon the resource being investigated. But it's critical to look at the surface and the subsurface in order to truly quantify exactly what is there and actually truly evaluate the reserve potential of these lunar resources. Thank you very much. And any questions, I'll try and answer them.
Yeah, thank you so much, Cliff. maybe let me ask one of the questions I always want to ask you. That is for a newcomer like Taiwan, how could we get into the game?
That's an interesting one, and that's why I'm drafting this document to send it to folks in Taiwan, in United Arab Emirates, to Australia, because space agencies, every nation seems to have a space agency now, but how can they contribute? And this is we look at the capability. Are there instruments under development that would be useful for quantifying these resources? Are there new developments in things such as radar that could be used? What about rover technology? Who is developing rover technology that could be part of the fleet to go to the moon and form this campaign? It's wide open, and it's what is Taiwan working on that they think that they have a specialty in, and that is something, because it's wide open. We have to have a campaign. We need multiple missions. We need to go to multiple locations. We go together as an international community. We can visit those locations. Interesting thing is that I presume you've heard of the ISEG-G, the International Space Exploration Coordination Group. They approached the League, Lunar Exploration Analysis Group, that I was chairing at the time, and wanted us to do a study, because their members had these missions going to the South Pole, and they were all interested in resource. So that study's available from the League website, but it's what data do we need and should be collected by each mission so that we can do prospecting. And that's what we came up with. Was well, you need to these types. We're not telling you what instruments to put on, but these are the data you are going to need in order to do that. And so that is one of the documents that I'm using to help in drafting this international prospecting campaign document. ESA has done a European Space Agency has done a similar study, and I'm using one of their documents as well. So I see this as a wide open opportunity for the world to go to the moon together and understand what resources are there. So it's not just one nation doing it, it's many nations doing it, but we're doing it with a common goal.
Yeah, you're not just an excellent spokesman, you're also an excellent salesman. You must come to Taiwan one day. After
I would love to. I would love to. So.
I mean, I want you to help us to knock on the door of the rich people in Taiwan, say, asking to invest in the moon.
There's a lot of opportunity in the moon right now, and I am convinced that it doesn't need space agencies to drive it. There are companies that want to go to the moon, that want to look at these resources. And to my science friends, I say we need to inform them, we need to help them. And some are saying, well, they're going to destroy the water ice and we'll never get to look at it. And I said, no, they're not. That's completely incorrect. The data that they will gather, if we do the campaign correctly and we do the mining correctly, will inform science in ways that just doing science missions never could.
Okay, I think that next step is to establish a Lunar Environmental Protection Agency.
No, I disagree with that as well. We've had that over here, because what are you protecting the lunar environment for, or who are you protecting it for? Because the environment is something that is aesthetic, but down here it supports life. On the moon, it doesn't do that. It doesn't support life, and so I think that we need to go forward together, have these discussions together with the people that want to exploit, if you like, the resources, people who want to use the resources, and the scientists that just want to understand the resources. But if we're all going to look at the resources, we can go together.
Very good. I think that we have. I hope we have a many chance to talk about this, over beer. Hopefully, in Taiwan.
Yeah. Well, it's going to take more than one. I'm telling you that.
Very good. Very good. Okay, Clive. Because time is up now, because we have the next talk at 5 minutes, and then as I said, if the audience have questions, they could write to me or actually send the email. I think they could find your email address very easily.
Well, I think it was on the title slide that I'll just flash back up again.
See Neal, see Neal at the Notre.
You can do see Neal at nd.edu, or you can use the one that is on that on the screen there, neal.1@nd.edu.
Yeah, and when you have this document ready, please send a copy to me. I will put it into the fortune cookie. That might be an easier way to sell, right?
Well, it would have to be a pretty big fortune cookie. So.
Tomorrow you go to the moon, I say.
Yes, I will do that, Ip, and I will make sure that this gets broadcast far and wide, because I really think this is the way forward, and this is something that has actually been started over here by the Artemis Accords. I don't know whether you've heard about the Artemis Accords, because this is the way the world can go to the moon together.
Mm-hmm. I think that the way for Taiwan to jumpstart, is really to find an angle, as you said, to find a place where people feel convinced that it's wide open still, You don't have to go back to the 50 years of lunar science. I mean, it's not the way to catch up. Yeah.
And it's with commercial lunar payload services these days, you can actually test your systems on the surface of the moon quite cheaply. So it's something else to remember there. But definitely, I will send you that document. And thank you, everybody, for listening. If you have questions, please email me.
Okay.
I may not answer them straight away, but I will get to them tomorrow.
Yeah. Thank you so much. Thank you so much.
Okay.
Yeah.
All right. Thank you.
Talk to you next time. Yeah.
Yeah. Stay in touch. Bye-bye.
Right.